Hey guys, so in this video I'll be talking about data augmentation in neural networks. Using data augmentation, we can create more training data without actually gathering more data. And there's many ways to create more training data, and it's dependent on what the neural network is training for. For example, if you're doing audio recognition like voice recognition, then maybe adding noise to the audio will make it more resilient against like background noise when it's actually being used in the real world. So in the example of handwritten digits, the image can be rotated, scaled, or random noise can be added to create new images. So for example, you can rotate it by 5 to 15 degrees. So for example here, and to the neural network, this looks like a completely different image, whereas to us it looks quite the same, obviously. And there's usually substantial gains to increasing the data quantity as well as the quality, because you are adding more variations into the data, and this allows the network to reduce overfitting, and it's kind of thought of as like a regularization technique, since creating more data kind of doesn't allow it to like overfit to super specific examples it's seen. So why is it effective? As I said, it reduces overfitting because it makes it harder to learn the small details and noise from training data when there's a large variety of rotated, scaled, and noisy images. And often you won't ever train on the same image twice, because if you rotate them and scale them, like for example from -15 to 15 degrees and then scale them and translate them and add noise, you'll pretty much always get new images. So that's one positive. As well as having a large amount of data is just always helpful in training networks because of the variety of cases, obviously. And it's like great because you can get a large amount of data without all of the time consuming and expensive work that's usually boring to do. So augmentation increases the diversity and exposes it to a wider range of variations and scenarios. So yeah, it lets you multiply training data. It's super useful for the network to find general patterns. But sometimes it does negatively affect the network. So if your training data is too noisy, for example, if you're doing voice recognition and you have too noisy data, then it might actually be better to reduce the noise, because the network might struggle to actually find useful general learnings from too noisy of data. So in some cases it's better to reduce the noise instead of make it even more noisy and augmented. So clean data helps it see clear patterns. Too much augmentation can mess up your network, as we'll see in a second, because it'll teach it unreasonable examples. For example, if you rotate this 180 degrees and have an upside down 5, it won't really make sense. So yeah, you gotta find a nice balance in between. And to test the effectiveness, I just created a simple network with these neurons, so 784 input, because we have 28 by 28 images from the MNIST data set. And then it goes to 128, 64, 32, and then 10 neurons at the end for the output. There's no dropout and no other regularization. So no L2 regularization, just this augmentation. And this is the graph I created. So you can see the values in here is the percentage translated. So 5% moved up and down or left and right. And then, oh no, this is 5% moved X, and then this is 5% moved up Y. And then this is the degrees rotated. So -5 to 5 degrees rotation. And the yellow one is the strongest data augmentation. We can see that it's not the best, and it takes longer to converge than no augmentation, which is blue. The blue one kind of converges quickly, and then it just stays there for like a long time at a bit over 97.5%. But the one with slight augmentation with the correct balance is able to converge much higher. Like this is 0.5%, but the difference is much bigger in bigger, deeper networks. So for this network, we saw that it's 0.5 degrees, This is running for 330 epochs. Um, this study here wrote a paper where they conducted a study on this, and they were using CFAR10 instead of MNIST, and this is like a much more complicated, like colored images, and they said that the results showed the full stage data augmentation framework leads to a significant improvement of classification accuracy for deep convolutional neural network models, and the average classification accuracy of CFAR10 increased from 85.7 to 93.5. So as we can see, it's much more substantial in larger networks. CFAR10 is one example of this. So yeah, now we'll look at a bit of code. So this is just a super simple script. It's literally just this many lines. It uses Torch to do classification, but here we can, this is where it's implemented, and you can look at the code on my GitHub. I'll leave a link in the description. But here you can set the degrees, so set it to this number to 15, and then set this to like 0.05 or 0.01 for more translation, and then here you change the image to self.transform image, so it'll transform it with that. And so when you train and get mini batches, you'll get more variations in your data. And in this script, you can also add dropout. So I have a dropout variable somewhere down here. I can't find it, but yeah, you can change learning rate and mess around with it. And here you can see the output I got that went up to this amount. This is with no data augmentation, so it leveled out at 97. And yeah, that's pretty much it. At this GitHub, you can also look at some other scripts as well. This is a simpler neural network script if you want to read through it and learn more about how they work. This is without using the complicated Torch stuff and just using lower level stuff and just tensors and like tensor math to make it run. So yeah, thank you for watching and have a great day.